The definition of an eigenvector is that it's a non-zero vector such that a matrix times that vector just returns a scalar multiple. All that A does to that vector is just stretch it. So geometrically, you can see that it just takes an original vector here and then makes it either longer or shorter depending on this value of lambda. Now, lambda is referred to as the eigenvalue that's associated with that eigenvector. In the last section, we saw that if you can write your basis in terms of eigenvectors, then working with the matrix A becomes pretty straightforward. And that's going to be our goal, is to find an eigenvector basis for our matrix so that calculations we have to do become pretty easy. Now, just as a very simple example of this, when we study dynamical systems, every power of a matrix that we use is essentially that many steps down into the future. So if we ever need to calculate a to the power of 100, for example, that's generally an involved calculation. If you're in an eigenvector basis, then it just collapses down to scalar multiplication, which is really, really easy. So now the question is, well, how to actually determine eigenvectors and eigenvalues? So how do we determine lambda and v, this eigenpair? All stems from the definition. So the definition that we wrote above said that we are looking for a non-zero vector v such that av equals lambda v. So what we're going to do is reorganize this equation. It'll be set equal to 0. We are going to take that second term and think of it as the identity matrix times v, because the identity matrix times any vector gives itself. So you can basically insert the identity matrix for free. We are assuming here that all of our matrices are square. We can factor out vector product, and it has to be on the right in this case because the v is on to the right. We are looking for solutions to this v. Now remember, the definition of this eigenvector says that this has to be non-zero. So we want non-trivial solutions to this equation. Non-trivial solutions means that this matrix A minus lambda I has to be not invertible, because if a matrix is invertible, it will only ever have the trivial solution to the homogeneous problem. So that gives us a condition. If a matrix is not invertible, that means the determinant of that matrix has to be equal to 0. So if we want to find a lambda v pair, it's a two-step process. Number one, we have to solve this equation. Determinant a minus lambda I is 0. And then number two, we then have to solve the equation a minus lambda I v equals 0, and we are looking for non-trivial solutions. And we use the values of lambda from step 1. I'm going to go through an example for you. So here's a matrix that we had done in a previous set of videos. 2 by 2 matrix. So step 1 is calculate the determinant of a minus lambda I, and lambda is just some constant. So if I form the matrix a minus lambda I, I'm essentially taking a subtraction of lambda down the diagonal of this original matrix. Let's solve the equation determinant a minus lambda I is 0. It's a polynomial equation for lambda. And in fact, this is a second degree polynomial equation. Sorry, I made an error here. This should be a 4 because it's 2 times 2. So this equation in particular, it's already in this nice factored form. So all I need to do is take a square root. Remember that the square root of some quantity squared is its absolute value. The square root of 4, this symbol represents a principal root. So this is a 2. So this ends up giving us two equations. 3 minus lambda is 2, and negative 3 minus lambda is 2. Lambda is 1, 3 minus lambda is negative 2, so lambda will be 5. This matrix A, it has 2 eigenvalues. So that's the first step. When I say solve determinant a minus lambda I is 0, this is a polynomial equation. In this particular case, it's a quadratic equation. Now, I have to solve a minus lambda I v equals 0 for each case of lambda. And remember that I want the non-trivial solutions. That means I'm always going to have to get a free variable in this. Start with one of the eigenvalues. It doesn't matter which one. I'll be now solving this equation. A minus I times V is 0 because the lambda is 1. And the matrix was 3, 2, 2, 3. So if I subtract 1 down the diagonal, I'll get 2, 2, 2, 2, 0, 0. I have one pivot. I get a free variable, just like I talked about. x2 is my free variable, so x1 will be negative x2 in this case. The eigenvector, x1, x2, negative x2, x2, I'm going to factor out a negative x2 because I want this to match up with what I did in the previous video. This time we use the eigenvalue of 5. You're going to be subtracting 5 down the diagonal of your original matrix, so you'll end up with a negative 2, 2, and a negative 2, 0 on both ends. So when you row reduce this, you should always see that one of your rows is duplicated because we need to have non-trivial solutions. In this particular case, x1 is equal to x2. So the eigenvector here, which is just x1, x2, is going to be x2, x2. I can factor out that free variable and I'll get a 1, 1. There are infinitely many eigenvectors. If we have a free variable, we have to have infinitely many vectors. How can I say there's just one eigenvector for my problem? The process of finding an eigenvector for a given lambda is essentially finding a basis for the null space of your matrix A minus lambda I. Solve A minus lambda I times some vector V is 0. And we would like to know all the solutions. The non-trivials are the ones we are looking for. We're going to say E subscript lambda is the null space of A minus lambda I, and we're going to call this the eigenspace for a given lambda. When we say an eigenvector, what we mean is a basis for this eigenspace. In the first case, when lambda was 1, this is the basis vector. That's what we are going to call the eigenvector. This is the basis vector. So this is what we are going to call the eigenvector for lambda equals 5. And this is the eigenvector for lambda equals 1. That's what we mean when we say find an eigenvector. So this matrix A had eigenvalue 1, so we'll call this lambda 1, and eigenvector 1, negative 1. It had an eigenvalue of 5 and a corresponding eigenvector of 1, 1. This matrix A does, in fact, have an eigenvector basis for R2. Once we have an eigenvector basis, it makes life easy when we want to do calculations.